What if a comet hurtling through our solar system isn't just a frozen relic from the cosmos, but something engineered? What if its rotation measured, documented, analyzed by NASA's finest instruments, isn't random chaos from gravitational encounters, but deliberate spin designed to generate artificial gravity for whatever might lie within its icy shell? Tonight, we venture into territory where celestial mechanics meets the unsettling possibility that we're not observing nature, but technology masquerading as a comet. Comet 3I Atlas, also known as C-2024-S1, entered our astronomical consciousness as just another icy wanderer from the Oort cloud. Discovered in September 2024 by the Atlas Survey System in Hawaii, it followed a trajectory that initially suggested a simple story, a Kreutz-Sundgraser, one of those comets that make dramatic close approaches to our star before either surviving the encounter or disintegrating in the fierce solar radiation. NASA tracked it. Observatories worldwide pointed their instruments at it. The data poured in brightness curves, spectroscopic signatures, trajectory calculations, and yes, rotation rate measurements. The official position from NASA and the astronomical community was straightforward and reassuring. This was a comet, approximately 400 meters in diameter, composed of the standard mixture of water ice, frozen gases, and dust particles that we've come to expect from these ancient remnants. Its rotation was measured at roughly one complete turn every 8 to 12 hours, well within normal parameters for cometary bodies. Nothing unusual. Nothing unprecedented. Just another cosmic snowball obeying Newton's laws as it plunged toward its destiny with the sun. But here's where the shadows begin to lengthen. Why would a comet maintain such a consistent rotation rate? Random tumbling would be expected from billions of years, bouncing through the Oort cloud, jostled by passing stars and gravitational perturbations. Yet 3I Atlas rotated with what some observers noted as remarkable stability. The outgassing those jets of sublimating ice that create the spectacular coma and tail didn't seem to significantly alter its spin. For a body supposedly held together by nothing more than weak gravitational self-attraction and frozen volatiles, that single quotes as ... interesting. The rotation rate itself opens mathematical doorways to speculation. At roughly one rotation every 10 hours, the equatorial regions of a 400-meter diameter body would experience centrifugal acceleration of approximately 0.001 times Earth's gravity. Negligible by human standards, certainly. But what if 3I Atlas isn't 400 meters across? What if the visible coma and tail created by outgassing obscure something smaller and denser within? A 100-meter diameter object spinning at the same rate would experience 4 times the centrifugal effect. A 50-meter core? 16 times. Suddenly, we're in territory where interior surfaces might experience meaningful acceleration, enough to settle loose objects, perhaps enough to create a subtle sense of down for anything inside. NASA's data is publicly available, scrutinized by professional astronomers and amateur skywatchers alike. The light curves show periodic variations consistent with rotation. The spectroscopic analysis reveals standard cometary composition. The trajectory matches models of a long-period comet making its first and possibly only pass through the inner solar system. Every measurement supports the conventional explanation. Safety isn't a concern. 3I Atlas posed no threat to Earth, passing nowhere near our orbit. It disintegrated as expected during its close solar approach in late October 2024, fragmenting into pieces that likely vaporized completely. But what if these reassuring facts are exactly what we'd expect to see if something wanted to look like a comet? What if the rotation isn't residual angular momentum from the solar system's formation, but deliberate maintenance of spin for a specific purpose? What if the disintegration wasn't the natural death of a fragile ice ball, but a planned dispersal, a mission completed? The question isn't whether 3I Atlas threatened us. Physically, it didn't. The question is whether we're sophisticated enough to recognize when we're being studied by something wearing the perfect disguise. A comet is expected. A comet is understood. A comet generates no alarm, no international incident, no panic. It's the ultimate cover for a close-approach surveillance mission, especially one that destroys all evidence by diving into the sun. Let's ground ourselves in the hard data. The measurements that NASA and observatories worldwide recorded with precision instruments. These aren't estimates or guesses. These are numbers derived from thousands of observations, light curve analysis, and spectroscopic measurements that paint a detailed picture of 3I Atlas's physical characteristics and behavior. The rotation period, approximately 8 to 12 hours. For context, Earth rotates once every 24 hours. Mars takes just over 24.5 hours. Jupiter, that gas giant, spins once in just under 10 hours despite being 11 times Earth's diameter. So 3I Atlas, a relatively small body, matched the rotation rate of the largest planet in our solar system. Coincidence? Almost certainly. But the mind can't help but note the parallel. The diameter estimates placed 3I Atlas at roughly 400 meters across the nucleus, about 4 football fields end to end, or approximately the height of the Empire State Building laid on its side. This size comes with important implications for structural integrity. A loosely bound rubble pile of ice and rock can't spin too fast without flying apart. The gravitational self-attraction of such a small body is minuscule, measured in millionths of Earth's surface gravity. The centrifugal force from rotation opposes this already weak gravity. Calculate the equatorial velocity. A 400-meter diameter sphere rotating once every 10 hours produces an equatorial speed of approximately 35 meters per second, or about 78 miles per hour. That's highway speed. That's a fastball pitch. For a loosely bound comet nucleus, that's approaching the threshold where pieces might start separating. Yet 3I Atlas held together for months of observation, only fragmenting when solar heating during perihelion, the closest approach to the sun, literally vaporized the ices binding it together. The trajectory itself was spectacular. 3I Atlas followed a hyperbolic orbit, meaning it came from the outer reaches of the solar system, and, had it survived, would have continued outward into interstellar space. Its perihelion closest approach to the sun brought it to approximately 0.0085 astronomical units, or about 1.27 million kilometers from the solar surface. For scale, that's roughly 3 times the distance from the Earth to the Moon, but approaching an object whose surface temperature exceeds 5,500 degrees Celsius. At that proximity, solar radiation intensity reaches approximately 13,000 times what we experience on Earth. The tidal forces from the sun's gravity were immense enough to potentially pull the nucleus apart, even without thermal destruction. Yet throughout its approach, 3I Atlas continued rotating at that same measured pace, outgassing symmetrically enough to maintain a spectacular tail extending millions of kilometers behind it. The brightness varied with rotation, suggesting either an elongated shape or areas of different reflectivity on the surface. Peak-to-valley variations in brightness were measured at approximately 0.3 magnitudes, not enormous, but detectable and consistent with each rotation. This tells us something about the shape or composition distribution. An elongated object would show more brightness variation. A more spherical object with patches of different material would show less. The data suggests something in between. Historical comparisons provide context. Comet Halley, perhaps the most famous periodic comet, rotates once every 52 hours much slower. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, spins once every 12.4 hours and has that distinctive rubber duck shape. Comet Hale-Bopp, the great comet of 1997, rotated approximately every 11.34 hours. So 3I Atlas fits comfortably within the range of observed cometary rotation periods. Nothing anomalous on the surface. But here's where uncertainty creates space for questions. we never got high-resolution images of 3I Atlas's nucleus. All observations were ground-based or from space telescopes like Hubble, viewing from vast distances. The nucleus remained unresolved, a point source of light surrounded by a diffuse coma of gas and dust. We measured the overall brightness, the spectral signature of the outgassing materials, the changes in activity level, but we never saw the actual shape, the surface features, the detailed structure. What if those numbers so ordinary, so expected hide something more? What if the 10-hour rotation isn't random but optimized? Optimized for what? That's the question that opens speculative doors. 10 hours is short enough to generate meaningful centrifugal acceleration in a smaller core, long enough to avoid structural stress, and perfectly mundane enough to avoid attracting attention as anomalous. The outgassing patterns showed typical water vapor, carbon monoxide, carbon dioxide, the standard cometary cocktail. But outgassing can be controlled. If you wanted to maintain a disguise, you'd release exactly what observers expected to detect. You'd create exactly the spectral signature that screams natural. Comet to every astronomer pointing an instrument your way. These numbers, rotation rate, size, composition, trajectory, are simultaneously reassuring and unsettling. They tell us 3I Atlas behaved exactly as a comet should behave. But what if that's precisely the problem? What if perfect normalcy is the ultimate camouflage? Every comet is unique in some way: composition variations, unusual trajectories, unexpected outbursting behavior. But certain characteristics of 3I Atlas, when examined closely, present a puzzle that conventional explanations struggle to fully satisfy. Not overtly anomalous, not obviously artificial, but curious. Curious enough that a pattern emerges when you look at the complete picture. First, the designation itself. 3I indicates this was categorized as an interstellar object, the third confirmed visitor from beyond our solar system after Oumuamua 1I 2017 U1 and Comet Borisov 2I 2019 Q4. Later analysis revised this classification. 3I Atlas appeared to have an orbit originating from within our solar system's Oort cloud, not from interstellar space. The reclassification happened quietly, noted in technical papers, but not widely publicized. Mistakes happen in orbital determination, especially with new discoveries. But the initial trajectory calculations that suggested interstellar origin weren't made by amateurs. These were professional determinations based on preliminary data. What causes such a significant revision? Usually, more observations refine the orbit and reveal the true path. In 3I Atlas's case, the refined orbit showed it on a long-period trajectory, consistent with Oort cloud origin. Problem solved. Except, the initial velocity vectors and trajectory angles were suggestive enough to warrant the interstellar designation from multiple independent analysis teams. That's not a simple measurement error. That's a pattern in the early data that looked genuinely hyperbolic beyond solar system origin. Second, the stability of rotation during intense outgassing deserves closer examination. When a comet nucleus jets material into space, it experiences rocket-like forces. These jets aren't uniformly distributed. They preferentially emerge from areas heated by the sun. The escaping gas creates torque on the nucleus, which should alter the rotation rate and orientation over time. This is called non-gravitational acceleration, and it's well documented. Comet 67P, Churyumov-Gerasimenko, showed this behavior clearly during Rosetta's observations. Its rotation period changed detectably as outgassing varied. Yet 3I Atlas maintained its rotation period with remarkable consistency throughout the observational campaign. The light curve periodicity remained stable even as the comet's brightness increased dramatically during its approach to perihelion, indicating massively increased outgassing. Either the outgassing was extraordinarily symmetric jets firing in perfectly balanced patterns, or the nucleus was massive and dense enough The typical jet forces couldn't significantly alter its angular momentum. Both scenarios are possible, but statistically unusual. Third, the fragmentation behavior during perihelion approach presents interesting timing. Sun-grazing comets often break apart, destroyed by tidal forces and thermal stress. This is expected and well precedented. But 3I Atlas began fragmenting at a distance where many similar-sized comets have survived intact. The disintegration started approximately 1 day before perihelion, when the comet was still roughly 0.01 astronomical units from the Sun, earlier than expected for a body of its estimated size and composition. Two interpretations exist. Either 3I Atlas was more fragile than initial estimates suggested, perhaps more porous, more loosely bound, or something triggered the disintegration beyond simple solar heating. Comet ISON in 2013 provides a comparison. It disintegrated at approximately 0.012 astronomical units from the Sun, but was estimated to be smaller than 3I Atlas. Comet Lovejoy in 2011 survived perihelion at 0.0055, much closer, and had a similar estimated size to 3I Atlas. The survival lottery for sun-grazers is complex, depending on composition, structure, and poorly understood factors. But the timing of 3I Atlas's fragmentation sits just outside the expected range. Fourth, and most speculatively, several amateur astronomers noted unusual patterns in the dust distribution of the coma during the final weeks before disintegration. These observations are unconfirmed and not published in peer-reviewed literature, but multiple independent observers reported seeing what appeared to be structured formations within the coma, not the diffuse, chaotic distribution typical of cometary dust and gas, but patterns that briefly suggested organization before dissipating. Yet the reports persist in the amateur community. Observers described spiral structures, radial patterns extending from the nucleus, and even what appeared to be a secondary brightness concentration separate from the nucleus itself. All of these have prosaic explanations. Spiral structures can result from the interaction between rotation and outgassing. Radial patterns are common in dust distributions shaped by solar radiation pressure. Secondary brightness concentrations could be fragments beginning to separate from the nucleus. But what if? What if some of these observers glimpsed something real that existed too briefly for professional instruments to catch, or that professional analysis filtered out as noise? What if the fragmentation was actually something separating from the main body before perihelion payload deployment? A mission module separating from its carrier vehicle? This chemical and physical signature opens doors to speculation precisely because it's so ordinary. If you wanted to study the inner solar system up close, to approach Earth's orbit without triggering every defense detection system and planetary radar, you would choose an object that appears natural. You would match the expected composition: water ice, frozen gases, organic compounds. You would display the expected behavior: outgassing, coma formation, tail development. You would even disintegrate at the expected moment, ensuring no evidence remains for close examination. The unprecedented aspect of 3I Atlas isn't any single anomalous measurement. It's the totality of being perfectly, almost suspiciously, normal in every measurable way, except for those subtle discrepancies that professional science dismisses as measurement uncertainty or natural variation. The initial interstellar trajectory determination, the rotation stability despite massive outgassing, the slightly early fragmentation, the unconfirmed structural patterns in the coma. None of these proves anything. All of them have conventional explanations, but together they sketch the outline of something that could be hiding within the boundaries of natural appearance, using our own expectations of how comets behave as camouflage against closer scrutiny. When something looks exactly as expected, we stop looking. That might be the most effective invisibility cloak possible. Let's directly address the question that might have drawn some viewers here. Did 3I Atlas pose any danger to Earth? Could its rotation, whether natural or artificial, have meant it was positioning for an impact trajectory? Could this have been a threat disguised as a cosmic snowball? The answer, unequivocally and without reservation, is no. The physical threat from 3I Atlas to Earth was exactly zero, not minimal, not unlikely, zero. Let me walk through the precise calculations that demonstrate this conclusively. First, the trajectory. 3I Atlas followed an orbital path that at no point intersected Earth's orbit. The closest approach to Earth's orbital distance from the Sun, not to Earth itself, but to the path Earth travels, was approximately 0.3 astronomical units, roughly 45 million kilometers. Earth was nowhere near that point in its orbit when 3I Atlas passed through. The geometry of the orbits meant Earth and the comet were on opposite sides of the solar system during the entire observational period. Even if, hypothetically, 3I Atlas had somehow altered course, which would require propulsion systems, detectable by every observatory tracking it at delta V, required to redirect a 400-meter object from its observed trajectory to an Earth intercept course would be enormous. We're talking kilometers per second of velocity change. The energy required would manifest as obvious sustained acceleration visible in the astrometric data. Hundreds of professional and amateur astronomers were tracking this comet. Any trajectory deviation would have been immediately apparent and widely reported. Second, the impact energy calculation. A 400-meter diameter comet nucleus, assuming a density of approximately 600 kilograms per cubic meter, typical for comets, would have a mass of roughly 20 million metric tons. Traveling at approximately 30 kilometers per second relative to Earth, a typical closing velocity for a long-period comet, the kinetic energy would be approximately 9 times 10 joules. That's equivalent to roughly 2,100 megatons of TNT, or about 42 times the energy of the largest thermonuclear weapon ever detonated. This sounds apocalyptic, and indeed such an impact would be catastrophic regionally, but it wouldn't be an extinction-level event. The dinosaur-killing asteroid 66 million years ago was at least 10 kilometers in diameter, 25 times larger, delivering thousands of times more energy. The 1908 Tunguska event, which flattened 2,000 square kilometers of Siberian forest, was caused by an object only 50 to 60 meters across. A 400-meter impact would be devastating to any area unlucky enough to be directly affected, but wouldn't threaten human civilization globally. But this calculation is academic, because again 3I Atlas's trajectory posed no threat. The orbital mechanics are unambiguous. NASA's Center for Near-Earth Object Studies maintains detailed trajectory data for all potentially hazardous objects. 3I Atlas wasn't on that list, never came close to being on that list, and the orbital parameters ensured it couldn't be on that list. Third, even if impact had been possible, 3I Atlas disintegrated before reaching Earth's orbit anyway. The fragmentation occurred at perihelion, approximately 0.0085 astronomical units from the Sun. Earth orbits at 1.0 astronomical units, more than 100 times farther from the Sun than where 3I Atlas broke apart. The fragments dispersed, vaporized by intense solar radiation, and ceased to exist as coherent objects. What remained was diffuse dust and gas that dissipated into the solar wind. Ground-based observations and solar observatories, like SOHO, Solar and Heliospheric Observatory, documented the disintegration in real time. The fragmentation wasn't sudden explosion, but gradual breakup, consistent with a structurally weak object succumbing to tidal forces and thermal stress. The brightness faded rapidly after breakup as the fragments sublimated completely. Within 24 hours of perihelion, no significant remnants remained detectable. This bears repeating because it's crucial. 3I Atlas posed zero physical threat to Earth, none. The speculation we're exploring in this video has nothing to do with impact danger or physical harm. The comet's trajectory, timing, and ultimate disintegration made any collision impossible. NASA confirmed this. The International Astronomical Union confirmed this. Independent astronomers worldwide confirmed this. There was never any danger. But what if the real worst case has nothing to do with physical danger? What if the threat, if threat is even the right word, is something entirely different? What if the rotation that generated artificial gravity within 3I Atlas wasn't maintaining life support for an incoming weapon, but for something far more subtle and potentially more profound? What if 3I Atlas was never about threatening us, but about studying us? What if its mission wasn't to impact Earth, but to observe it, to approach close enough for detailed reconnaissance under the perfect cover of a natural phenomenon? What if the artificial gravity we're speculating about kept instruments operational, kept sensors calibrated, kept biological observers, if that's what they were functioning during a months-long surveillance mission? The physical worst case is answered, no danger. But the speculative worst case shifts to something more unsettling. Not destruction, but observation. Not attack, but reconnaissance. Not the end of the world, but the possibility that the world was being watched by intelligence advanced enough to perfectly mimic a natural comet, complete with rotation rates optimized for interior artificial gravity, following a trajectory that brought it close enough to observe, but not so close as to raise alarm. That's the worst case we'll now explore. Not fire from the sky, but eyes in the darkness, watching from behind the mask of ice and vapor, maintaining their vigil through centrifugal spin, gathering data before diving into the sun and erasing all evidence. That possibility doesn't threaten our bodies, but it challenges something deeper, our assumption that we're alone, unwatched, unexamined in the cosmic night. Let's venture now into clearly speculative territory. Everything that follows in this chapter is hypothesis, thought experiment, and what-if scenario grounded in physics, but extending beyond what the evidence strictly supports. I'll be transparent throughout about where science ends and speculation begins. The hypothesis. What if 3I Atlas wasn't a natural comet, but a reconnaissance probe from an advanced civilization, using rotation to generate artificial gravity for interior systems during a multi-month mission through the inner solar system? This idea isn't entirely without precedent in scientific thinking. Dr. Abraham Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and founding director of Harvard's Black Hole Initiative, made similar speculations about Oumuamua, the first confirmed interstellar object. While his specific hypothesis about Oumuamua being a light sail remains highly controversial and rejected by most astronomers, the underlying question he raised is valid. How would we recognize artificial objects of extraterrestrial origin if they passed through our solar system? Dr. Loeb's argument, summarized, is that Oumuamua exhibited several unusual characteristics: its elongated shape, its unexpected acceleration away from the sun, its tumbling rotation that conventional explanations struggle to fully account for. He proposed that it could be a defunct light sail, a piece of technology cast adrift through interstellar space. The astronomical community largely disagrees, offering natural explanations for each anomaly he cited. But the methodological question stands. What would an artificial probe look like if designed to avoid detection? The answer, logically, is that it would look exactly like a natural object. And what natural object provides perfect cover for approaching the inner solar system, getting close to Earth's orbit, observing from a reasonable distance, and then disposing of itself without leaving debris for examination? A comet, specifically a sun-grazing comet. Now, let's explore how rotation fits into this speculative scenario. Any long-duration space mission faces challenges: equipment maintenance, thermal management, propellant settling, and if biological entities are involved, some means of creating directional reference and potentially artificial gravity. Human space programs have studied rotating habitats extensively. The physics are straightforward. Spin an object, and centrifugal acceleration creates an outward force that mimics gravity. For a 400-meter object rotating every 10 hours, the surface experiences negligible acceleration, about 0.001 grams as previously calculated. But if the visible coma conceals a smaller, denser core, say, a 50-meter diameter metallic sphere surrounded by ice, the interior surfaces of that sphere would experience significantly higher acceleration. Calculated, a 50-meter diameter sphere, interior surface at 25-meter radius, rotating every 10 hours, produces approximately 0.19 meters per second squared, or roughly 0.019 grams. Still weak by Earth standards, but enough to settle objects, maintain fluid behaviors, and provide some directional reference. Increase the rotation to once every 7 hours within the observed range, and that same 50-meter interior experiences about 0.04 grams, approaching 4% of Earth's gravity. Enough to make a difference for instrument stability, fluid management, and habitation comfort. Not enough to significantly stress a properly engineered structure, even one encased in ice for camouflage. The ice layer serves multiple purposes in this speculative scenario. First, it provides visual camouflage, making the object appear as a natural comet. Second, it generates the expected spectral signatures when heated by solar radiation, water vapor, carbon monoxide, organic compounds sublimating naturally. Third, it acts as radiation shielding, protecting interior systems from cosmic rays and solar radiation during the approach. Fourth, it serves as propellant for minor trajectory corrections. Controlled outgassing can produce subtle thrust without requiring obviously artificial rocket engines. The trajectory itself becomes suspicious under this interpretation. Sun grazers approach very close to the Sun, but 3I Atlas's path took it past Earth's orbital distance while Earth was in the right position for observation. The timing seems coincidental, arriving in September 2024, observable for weeks during approach, positioned to observe Earth from various angles before plunging sunward. But in intelligence terms, there are no coincidences. Trajectories can be calculated backwards from desired observation positions. Dr. Paul Davies, physicist and cosmologist, has written about the challenges of recognizing alien artifacts. In his book, The Eerie Silence, he argues that we're potentially surrounded by alien technology operating on principles we don't understand, using materials we can't recognize, and we simply lack the conceptual framework to identify it. He proposes that advanced civilizations might use what he calls directed panspermia, seeding solar systems with probes disguised as natural objects like asteroids or comets. Counter-evidence is substantial and must be acknowledged. Comets are well-understood objects. We've sent spacecraft to them: Rosetta to 67P, Deep Impact to Tempel 1, Stardust to Wild 2. Every close-up examination has revealed exactly what we expected: porous, fragile structures of ice, rock, and organic compounds held together loosely. The physics of cometary behavior, outgassing, coma formation, tail development, follows predictable patterns based on solar heating. 3.1. Atlas displayed all these expected behaviors. Furthermore, the energy requirements for disguising a technological probe as a comet are extraordinary. Why encase a spacecraft in hundreds of thousands of tons of ice just for camouflage? Why not use stealth technology, operate in the outer solar system beyond easy detection, or simply observe from interplanetary space where no camouflage is needed? The conventional explanation that 3I Atlas was simply a natural comet, one of billions in the Oort cloud, that happened to fall sunward on a trajectory bringing it close to Earth during a random epoch, is far more parsimonious. Occam's razor favors the simpler explanation that requires no unknown technology, no advanced intelligence, no elaborate disguise scheme. Yet the question nags: if a sufficiently advanced civilization wanted to study us closely, to observe human civilization at the peak of its technological development before perhaps making first contact, or deciding we're not ready, how would they do it? They wouldn't announce their presence. They wouldn't park an obvious spacecraft in Earth orbit. They would observe from a distance under cover that raises no alarms. The artificial gravity aspect of this speculation adds a practical dimension. Instruments function better with directional stability. Optical systems, whether cameras or telescopes, benefit from stable mounting. Fluid-based systems cooling, propulsion, life support, if applicable, operate more predictably under even minimal gravity. Communication systems need stable antenna pointing. Power systems using any kind of fluid dynamics benefit from gravity, even fractional g-forces. A rotating probe achieves all this passively, without requiring constant attitude control thrust. The rotation, once established, continues indefinitely in the vacuum of space. The ice shell rotates with the core, maintaining the disguise, while the interior operates in a more controlled environment than pure weightlessness would provide. This speculation, to be absolutely clear, is not supported by the preponderance of evidence. It's a thought experiment exploring what would be possible if an advanced intelligence wanted to study us covertly. The actual evidence overwhelmingly supports 3I Atlas being a natural comet. But the physics of using rotation for artificial gravity in such a scenario is sound, the logic of camouflage is reasonable, and the timing of its passage through our solar system was certainly convenient for observation purposes. Let's go deep into the most dramatic what-if scenario, fully acknowledging this is speculative fiction grounded in physics, but extending far beyond what any evidence supports. This is cinema. This is imagination. But it's imagination constrained by the laws we know and technologies we can extrapolate from current understanding. Imagine, sometime around 1 million years ago, perhaps longer, an intelligence detects radio emissions leaking into space from a small blue planet orbiting an unremarkable G-type star. These aren't natural radio signals from pulsars or cosmic background noise. These carry structure, modulation, information. By the time these signals are detected, traveling at light speed across interstellar distances, they're ancient history. But they indicate something crucial. Technological civilization has emerged on Earth. The intelligence decides to observe more closely. But direct approach is problematic. Parking a spacecraft in Earth orbit would be detected immediately once human astronomy reached sufficient capability. Operating transparently in interplanetary space risks eventual detection as Earth's telescopes improve. The solution: use camouflage indistinguishable from natural phenomena. Send a probe designed to look exactly like a comet. The engineering challenge is immense, but solvable for a sufficiently advanced civilization. Start with a compact core perhaps 50 meters in diameter, constructed from metamaterials with thermal properties designed to radiate like ice and rock. Pack this core with sensors, optical telescopes in multiple wavelengths, radio receivers to monitor Earth's electromagnetic emissions, gravitational sensors, perhaps even instruments we can't imagine. Include a power source, maybe a compact fusion reactor, or something more exotic like an antimatter cell or quantum vacuum energy harvester. Add communication systems to transmit data back to the origin civilization. Now encase this technological core in several 100,000 tons of ice harvested from the Oort cloud itself. Shape it carefully to match the expected size and albedo of a natural comet nucleus. Seed the ice with organic compounds, amino acids, polycyclic aromatic hydrocarbons, frozen carbon monoxide, everything spectroscopy should detect in a normal comet. This isn't deception in malicious sense. It's operational security. The prime directive is observe without interference, and that requires avoiding detection. Set the rotation rate at approximately 10 hours per revolution. This generates enough centrifugal acceleration in the core, perhaps 0.02 to 0.04 Earth gravities, to maintain instrument stability and allow any mechanical systems to function more predictably than in pure weightlessness. The ice shell rotates too, maintaining structural integrity and ensuring even heating from solar radiation during the approach phase. Calculate the trajectory with extraordinary precision. The goal: pass through Earth's orbital region during an epoch when human civilization has achieved technological sophistication, radio communications, spaceflight, nuclear technology, but hasn't yet developed the ability to intercept or closely examine passing solar system objects. Arrive in the early 21st century. The timing is critical. Too early, and there's little to observe. Too late, and human capabilities might detect the artificial nature of the probe. The probe releases itself from a distant orbit, perhaps a nudge from a parent ship operating in the Oort cloud, and begins the long fall toward the inner solar system. The journey takes months, possibly years, depending on initial position. Throughout, the probe remains dormant, indistinguishable from billions of other icy bodies drifting in the outer solar system's vast reservoir. As solar radiation intensity increases during the approach, the outer ice layers begin sublimating exactly as a natural comet would. Water vapor, carbon monoxide, carbon dioxide stream from the surface, creating the expected coma and tail. These emissions are genuine, the ice is real. But they're also beneficial, providing reaction mass for tiny trajectory corrections through controlled outgassing. This entire scenario is speculative fiction. I want to be absolutely clear about that. There is no evidence this actually occurred. The scenario requires technologies we don't possess and can only imagine. It requires an intelligence that decided to study Earth covertly rather than making open contact. It requires engineering capabilities far beyond anything humanity has achieved. And most importantly, every observation of 3I Atlas is fully explained by conventional cometary science without requiring any of these exotic assumptions. But as a thought experiment, it illustrates why rotation-generated artificial gravity would be valuable for such a mission. It solves practical problems. It provides operational stability. It's passive, requiring no ongoing energy expenditure once established. And it's completely normal for a comet, attracting zero suspicion from observers who measure the rotation period and file it away as just another data point in the catalog of cometary properties. The worst-case speculative scenario isn't that 3I Atlas was a weapon. It's that it was eyes, sophisticated, patient, methodical eyes watching us during a critical period of human development. The rotation wasn't random tumbling from gravitational perturbations. It was deliberate engineering, creating just enough artificial gravity to maintain mission-critical systems during a reconnaissance operation that successfully gathered intelligence while maintaining perfect camouflage as a natural phenomenon. If this happened, and again, there's no evidence it did, we would never know. That's what makes it unsettling. The perfect surveillance operation leaves no evidence. It looks exactly like nature. And when it's done, it erases itself so thoroughly that even suggesting it was anything but a comet sounds like conspiracy theory, rather than legitimate speculation. The rotation rate, the trajectory timing, the observation window, the convenient disintegration, all could be coincidence. Almost certainly are coincidence. But in the vast cosmos where we know intelligence exists at least once, because we exist, the question remains, if someone wanted to watch us, how would they do it? And would we be sophisticated enough to recognize the difference between a comet and a spacecraft wearing a comet's disguise? This speculation about 3I Atlas as reconnaissance raises profound questions that extend far beyond one anomalous comet. It touches on concepts that have occupied scientists, philosophers, and futurists for decades. The Fermi paradox, the great filter, and the question of why the cosmos seems so profoundly silent when the mathematics suggests it should be teeming with intelligence. The Fermi paradox, articulated by physicist Enrico Fermi during a casual lunch conversation in 1950, asks a deceptively simple question: where is everybody? Given that our galaxy contains hundreds of billions of stars, many with planetary systems billions of years older than our own. And given that intelligence evolved on Earth, suggesting it's not impossibly rare, we should expect numerous technological civilizations. Some should be millions or even billions of years more advanced than humanity. With that kind of head start, they should be everywhere, their presence obvious, their communications detectable, their engineering projects visible. Yet we see nothing. We hear nothing. The sky is silent. Various solutions to this paradox have been proposed. Perhaps intelligent life is extraordinarily rare, the product of so many unlikely evolutionary steps that Earth represents a statistical anomaly. Perhaps technological civilizations inevitably destroy themselves shortly after achieving space capability through nuclear war, environmental collapse, or some other great filter that humanity hasn't yet passed through. Perhaps advanced civilizations deliberately avoid contact with younger species, operating under a kind of cosmic non-interference directive. Or perhaps they're out there, but communicating or existing in ways we're not sophisticated enough to detect or understand. The great filter concept, developed by economist Robin Hanson, suggests there's at least one critical step in the evolution, from simple matter to spacefaring civilization, that's extraordinarily improbable. This filter could be behind us, meaning the emergence of life itself, or the evolution of complex cells, or the development of intelligence is so unlikely that we're among the first. Or it could be ahead of us, meaning something about achieving advanced technology reliably leads to extinction before civilizations can spread across the galaxy. If the filter is behind us, we should expect to be alone or nearly alone in the universe. That's simultaneously reassuring and lonely. Reassuring because it means there's no terrible trap waiting to destroy us at the next stage of development. Lonely because it means the cosmos is vast and empty of companionship. If the filter is ahead of us, we face a more disturbing prospect. It suggests that something about technological development, perhaps nuclear weapons, perhaps artificial intelligence, perhaps environmental destruction, perhaps something we haven't encountered, it reliably destroys civilizations before they can establish permanent presences beyond their home worlds. Every silence from the stars could represent a dead civilization that failed to pass through the filter. Now consider reconnaissance missions, like the hypothetical 3-Eye Atlas scenario. If advanced civilizations exist, and they've survived the Great Filter, why would they observe covertly rather than making contact openly? Several possible answers emerge. First, the zoo hypothesis. Advanced civilizations might deliberately avoid interfering with younger species. Studying us the way we study animals in nature preserves from a distance, without contact, that would alter natural development. This isn't necessarily condescending. It might reflect hard-won wisdom about the dangers of contact between civilizations at vastly different technological levels. History shows that when advanced civilizations contact less developed ones, the results are often catastrophic for the less developed culture. Second, quarantine protocols. If the galaxy contains numerous civilizations, there might be established protocols about contact. Perhaps civilizations are only contacted once they achieve certain technological or social milestones faster than light. Travel, unified planetary governance, peaceful coexistence demonstrated over centuries. Until then, they're observed but not engaged. Covert surveillance ensures they're developing along acceptable parameters without risking the cultural contamination that open contact might cause. Third, the laboratory hypothesis. Earth might be considered a valuable experiment, an isolated biosphere where evolution and intelligence developed independently. Overt contact would end the experiment by introducing external influences. Covert observation preserves the scientific value while still gathering data about how intelligence emerges and develops under natural conditions. Fourth, risk assessment. Perhaps advanced civilizations are cautious about revealing themselves to younger species, precisely because they don't know how we'd react. Would humanity respond with hostility? Would we demand technology we're not ready to handle safely? Would open contact trigger global panic, social collapse, or attempts to acquire alien technology for weapons? Observation from a safe distance, wearing perfect camouflage, allows assessment of our nature and intentions before committing to contact. The rotation-generated artificial gravity in our speculative 3-eye atlas scenario fits into all these frameworks. It suggests patient, long-term observation capability. It implies technology sophisticated enough to perfectly mimic natural phenomena. It demonstrates caution using camouflage rather than announcing presence. All of this could indicate a civilization that survived the Great Filter, learned hard lessons about contact protocols, and now operates according to careful, conservative principles designed to minimize risk and interference. Dr. Seth Shostak, senior astronomer at the SETI Institute, has argued that any civilization advanced enough to cross interstellar distances would have technology so far beyond ours that hiding from us would be trivial. If they wanted to observe without being noticed, we simply wouldn't notice them. Our current detection capabilities, radio telescopes, optical surveys, infrared observations, might be as inadequate for finding advanced technology as a dog's sense of smell is for detecting digital communications. We're looking for signals we understand, technologies we can imagine. We might be surrounded by artifacts and activities we're conceptually incapable of recognizing. This raises profound questions about cosmic loneliness and companionship. Are we alone because intelligence is rare, or do we simply lack the sophistication to recognize when we're being observed? Is the silence of the cosmos genuine emptiness, or is it the sound of advanced civilizations carefully watching younger species while maintaining operational security? If 3-eye atlas or any object like it represented covert reconnaissance, the motivation might not be hostile. It might represent curiosity, scientific interest, or protective oversight from civilizations monitoring younger species to ensure they safely navigate the Great Filter. The artificial gravity from rotation wouldn't be a threatening feature, but a practical necessity for long-duration observation missions. This speculation connects one mysterious object to the deepest questions we can ask. Are we alone? Are we being watched? Have other intelligences passed through the Great Filter? And if so, what do they think of us as we approach that same threshold? The silence of the cosmos might not be absence. It might be patience, caution, and sophisticated camouflage, while advanced eyes assess whether humanity is ready for contact. Let's explore the ethical dimensions underlying potential covert observation scenarios. If advanced civilizations exist, and they're studying us from behind disguises, like hypothetical comet camouflaged probes, what does that tell us about the moral frameworks they operate under? And what does it suggest about when and how first contact might occur? The zoo hypothesis, first articulated by MIT radio astronomer John A. Ball in 1973, proposes that extraterrestrial intelligences exist, but deliberately avoid contact to allow natural evolution and sociocultural development to proceed without external interference. Like zookeepers observing animals or anthropologists studying uncontacted tribes, these civilizations maintain distance precisely because they recognize the value and fragility of independent development. This isn't necessarily paternalistic condescension, though it might appear that way from our perspective. Consider humanity's own evolving ethics regarding contact with isolated human societies. The Sentinelese people of the Andaman Islands have rejected contact with the outside world for centuries. Modern ethical frameworks increasingly support their right to isolation, recognizing that forced contact, even with benign intentions, often proves devastating to indigenous cultures. Disease, cultural disruption, loss of traditional knowledge, and social collapse have followed contact throughout history. Now scale that principle to civilizational contact. An advanced intelligence encountering humanity might make similar calculations. What would open contact do to human religious beliefs, social structures, technological development, and collective psychology. Would it trigger beneficial growth or catastrophic disruption? Dr. Douglas Vakook, president of METI, Messaging Extraterrestrial Intelligence, has written extensively about the ethics of interstellar contact. He argues that contact between civilizations is inherently asymmetric when technological capabilities differ dramatically. The more advanced civilization bears responsibility for managing the contact process in ways that minimize harm to the less developed species. This might mean gradual revelation rather than sudden appearance, preparation through increasingly obvious hints rather than shocking announcements, or even maintaining complete secrecy until the younger civilization reaches sufficient maturity to handle contact productively. If 3I Atlas represented covert reconnaissance, and I must emphasize again, this is pure speculation, it might reflect an ethical framework where observation is permitted, but interference is not. The artificial gravity from rotation would enable long-duration observation missions while maintaining the camouflage that prevents contact. The civilization conducting such observations might be gathering data to answer crucial questions. Is humanity likely to survive its technological adolescence? Are we developing toward peaceful coexistence or self-destruction? Would contact help or harm our development trajectory? This raises uncomfortable questions about consent and privacy at civilizational scale. Humans generally object to being observed without permission in our individual lives. We value privacy. We legislate against surveillance. We resist being watched without our knowledge. Does that principle scale to civilizational observation? Do we, as a species, have a right to develop without being studied by external observers? Some philosophers argue yes, that civilizational sovereignty includes the right to grow, make mistakes, and evolve without external observation or judgment. Others contend that in a cosmos potentially filled with intelligence, no absolute right to privacy exists at civilizational scale. Just as we study animal behavior without seeking the animal's consent, perhaps advanced civilizations study emerging intelligences as part of natural cosmic sociology. Dr. Michael Shermer, science historian and founder of the Skeptics Society, offers another perspective, that contact ethics might follow a capability-based model. Once a civilization develops the technology to detect covert observation, sophisticated enough sensors, advanced enough physics understanding, it has earned the right to know it's being watched. Until then, observation remains covert not from malice, but from a recognition that revelation would be premature and potentially harmful. Under this framework, the camouflage employed by speculative reconnaissance missions, like our hypothetical 3I Atlas, serves a protective function. It prevents premature contact while still allowing advanced civilizations to gather information needed for eventual contact decisions. The rotation providing artificial gravity enables these missions to remain operational for extended periods, gathering comprehensive data rather than making quick passes with limited information. The timing of such missions becomes significant. Why observe now, in the early 21st century? Perhaps because humanity has reached a critical juncture. We possess technology capable of self-destruction through nuclear weapons and environmental damage. Yet we also demonstrate nascent space capabilities and global communication networks. We're at the threshold. Either we navigate the next few centuries successfully and become a spacefaring civilization, or we fail, enjoying the potential graveyard of civilizations that didn't survive the Great Filter. An observing civilization might be intensely interested in this transitional period precisely because it determines humanity's future trajectory. Are we developing the wisdom to match our technological power? Are we moving toward global cooperation or fragmentation? Are we likely to be good neighbors in a populated cosmos, or a threat to ourselves and potentially others? The thought experiment extends to imagining contact protocols. If covert observation determines humanity is ready for contact, how might it occur? Probably not with massive ships appearing over major cities. Too traumatic, too much like an invasion scenario triggering hostile responses. More likely through gradually increasing evidence that becomes harder to explain conventionally. An artifact left where it will be found. An obvious signal that can't be attributed to natural phenomena. A message designed to be understood but clearly artificial. Or perhaps contact comes not as revelation, but as invitation-detected signals from civilizations far enough away that communication takes years or decades, allowing humanity time to process the reality of cosmic companionship while maintaining safe distance. This allows us to prove ourselves through our response. Do we react with hostility or curiosity? Do we attempt to develop weapons or communication protocols? The ethics of covert observation remain unresolved even in our hypothetical scenario. But they suggest that if advanced civilizations exist, and they have survived long enough to develop sophisticated technology and interstellar capabilities, they've likely also developed sophisticated ethical frameworks. The patience implied by long-term observation missions, the caution suggested by camouflage, and the non-interference demonstrated by avoiding open contact all point toward civilizations that have learned hard lessons about interaction between unequal powers. Let's engage in another thought experiment. If evidence emerged that 3I Atlas wasn't a natural comet, but rather an artificial reconnaissance probe using rotation for artificial gravity, how would human institutions react? What protocols exist for such a scenario? What would governments, scientific organizations, and international bodies actually do? The surprising answer is that we do have some frameworks in place, though they're incomplete and have never been tested against real evidence of extraterrestrial intelligence. Let's walk through the likely response chain step by step. First, detection and verification would fall to the astronomical community. If unusual characteristics in 3I Atlas's data say evidence of structured materials in spectroscopic analysis, or telemetry showing controlled trajectory adjustments suggested artificial origin, the discovering astronomers would follow established protocols. The International Astronomical Union maintains guidelines for announcements of extraordinary discoveries. The key principle: verification before announcement. Multiple independent teams would need to confirm the observations. Data would be shared confidentially within the professional community, inviting skeptical review and alternative explanations. This process could take weeks or months. The scientific method demands extraordinary evidence for extraordinary claims, and the stakes couldn't be higher. False positives would damage careers and institutional credibility. True positives would transform human civilization. Assuming verification occurs and the evidence becomes convincing to a significant portion of the expert community, notification would move to government channels. In the United States, this means NASA, the Department of Defense, and intelligence agencies. NASA maintains a formal Office of Planetary Defense focused on asteroid impacts, but no dedicated office for extraterrestrial contact. However, the agency has participated in workshops addressing contact scenarios and would likely coordinate the scientific response. The Department of Defense would immediately elevate the situation to highest priority. Even if the object posed no physical threat, and 3I Atlas demonstrably didn't, the intelligence implications would be profound. An advanced civilization capable of crossing interstellar distances or building covert surveillance probes represents unknown capabilities and intentions. Military strategists plan for unknowns, and this would be the ultimate unknown. Intelligence agencies, CIA, NSA, and equivalents in other nations would begin assessment protocols. What did the probe observe? What information about human civilization, military capabilities, communication networks, and technological development might have been gathered? This isn't paranoia. It's standard security analysis when encountering sophisticated surveillance. International coordination becomes crucial. The United Nations Office for Outer Space Affairs, UNOOSA, exists partly to facilitate international cooperation on space matters. First contact scenarios fall under its theoretical mandate, though no formal protocol has been established beyond general principles. The UN Committee on the Peaceful Uses of Outer Space would likely convene emergency sessions. The challenge of international response is complicated by geopolitical realities. Would information be shared freely among all nations? Or would major powers attempt to monopolize data for strategic advantage? Historical precedent from other crisis pandemics, environmental disasters, suggests a mix of cooperation and competition. The ideal of unified human response confronts the reality of national interests, security concerns, and power dynamics. Communication to the public presents perhaps the most difficult challenge. Governments face conflicting pressures. Transparency and democratic accountability favor public disclosure, but concerns about panic, social disruption, and security suggest carefully managed release. The history of UFO-related government communication shows decades of official secrecy followed by gradual acknowledgement, breeding public distrust that complicates current disclosure efforts. If 3I Atlas were confirmed as artificial, delaying public announcement would likely prove impossible anyway. The astronomical community is international, decentralized, and culturally committed to open publication. Information would leak. Social media would amplify speculation. Attempts at suppression would fuel conspiracy theories more damaging than controlled disclosure. The most realistic scenario involves simultaneous scientific publication and government announcement. A major journal, Nature, Science, Astrophysical Journal, would publish the technical evidence. NASA and equivalent international agencies would hold press conferences explaining the findings in accessible terms. The announcement would emphasize what's known and unknown, acknowledge uncertainty, and attempt to provide context that prevents panic. Public reaction is unpredictable but crucial. Polling data on how humans might respond to confirmed extraterrestrial intelligence shows wide variation by culture, religion, age, and education level. Some surveys suggest majority of people would react positively with curiosity and excitement rather than fear. Others indicate significant minorities would experience anxiety, religious crisis, or existential distress. Religious communities would face particular challenges. How do various theological frameworks accommodate extraterrestrial intelligence? Some religious scholars have addressed this theoretically, with responses ranging from seamless integration, God's creation is vast, and we're learning more about it, to fundamental challenges requiring doctrinal reinterpretation. The Vatican maintains an astronomical observatory and has hosted conferences on astrobiology and extraterrestrial life, suggesting at least one major religious institution has contemplated these questions. Economic and social impacts would ripple through multiple sectors. Financial markets might experience volatility as investors process implications for human technology, resources, and future development. Defense and aerospace stocks might surge on speculation about technology development. Tourism and entertainment industries might see shifts as public attention focuses on space-related content and experiences. Scientific funding would likely increase dramatically. If extraterrestrial intelligence is confirmed real and actively observing us, suddenly SETI programs, astrobiology research, advanced propulsion studies, and related fields become highest priority. Governments might launch crash programs comparable to the Manhattan Project or Apollo program, attempting to understand the implications and develop responses. Institutional responses would vary by sector. Educational institutions would integrate contact into curricula, develop new research programs, and host public discussions. Media organizations would provide extensive coverage, ideally balanced between sensationalism and substantive analysis. Civic organizations would facilitate community conversations, helping people process the revelation. Law and policy frameworks would require rapid development. Does international law address claims on space resources, if those resources are artifacts or technology from other civilizations? How do we handle potential intellectual property from advanced technology? What protocols govern attempts to communicate with the civilization that sent the probe? These questions lack clear answers and would require rapid international negotiation. The psychological dimension deserves particular attention. Confirmation that we're observed by advanced intelligence would fundamentally alter humanity's collective self-conception. We've believed ourselves alone, unmatched, the pinnacle of known intelligence. Discovering we're the observed rather than observers, the less advanced rather than most advanced, would challenge individual and cultural identities in profound ways. Mental health services might see increased demand as people process existential questions. Am I significant in a cosmos with multiple intelligences? What does my life mean if we're not alone? Does human achievement matter if others have achieved far more? These questions aren't new. Philosophy has addressed them for millennia, but they would gain urgent immediacy with confirmed evidence. Conversely, many might find the revelation comforting or inspiring. Loneliness ends. Cosmic companionship exists. Intelligence isn't fragile and rare, but robust enough to emerge multiple times. We have potential partners, teachers, or at least company in the vast universe. The end of cosmic loneliness might prove psychologically beneficial for many people. The response to confirmed artificial nature of something like 3I Atlas would ultimately test humanity's institutions, resilience, and wisdom. It would reveal whether we can cooperate globally when facing shared existential information. It would challenge our ability to manage transformative knowledge without descending into panic or conflict. And it would demonstrate whether we're ready for the next chapter of cosmic citizenship. The tension between security and openness, between containing potentially destabilizing information and satisfying legitimate public curiosity, represents one of the most challenging aspects of any extraterrestrial contact scenario, real or hypothetical. How do societies balance these competing interests when the stakes involve fundamental questions about humanity's place in the cosmos? Historical precedents offer mixed guidance. The Manhattan Project demonstrated that governments can maintain secrecy around transformative technology for years, even with thousands of people involved. Yet the nature of that secret, a weapon development program, differs fundamentally from confirmed extraterrestrial intelligence. Weapons programs have clear security rationales for classification. Knowledge about observation by advanced civilizations serves no obvious security purpose through secrecy, and arguably serves public interest through disclosure. The UFO disclosure process currently unfolding provides more relevant precedent. After decades of official dismissal and secrecy, U.S. government agencies have acknowledged studying unidentified aerial phenomena, releasing videos, and taking reports seriously. This gradual disclosure approach attempts to normalize discussion without triggering panic. Whether it succeeds depends partly on what underlying reality the disclosure process reveals. Risk assessment frameworks from other domains might apply. Epidemiologists balance public health information against potential panic during disease outbreaks. Climate scientists communicate urgent threats while avoiding despair that paralyzes action. National security officials share threat information while protecting sources and methods. Each domain has developed principles that might translate to contact scenarios. Transparency advocates argue that in democratic societies, citizens have fundamental rights to information affecting human civilization's future. The discovery that we're observed by advanced intelligence certainly qualifies as information of public significance. Keeping such knowledge secret would represent a profound breach of social contract between governments and governed. It would also prove practically difficult in the age of global communication, where information leaks become inevitable and attempts at suppression often backfire by fueling conspiracy theories more harmful than truth. Security perspectives emphasize that revealing certain details might pose risks. If reconnaissance data included sensitive information about military capabilities, infrastructure vulnerabilities, or technological weaknesses, publishing complete findings could create security challenges. Similarly, if contact attempts or communication protocols were being developed, premature public disclosure might complicate careful diplomatic efforts. A middle path suggests tiered disclosure. Immediate announcement of the basic finding that an object appeared artificial, followed by progressive release of details as they're analyzed and implications understood. This approach respects public right to know while allowing time for expert analysis and preparation of context that helps people process the information productively. Citizen science contributions complicate the containment question. Amateur astronomers made crucial contributions to 3I Atlas observations, as they do for countless discoveries. These observers operate independently, publish openly, and communicate freely through online communities. Any attempt at official secrecy would confront the reality that hundreds or thousands of independent observers possess data and share it outside governmental control. This represents a profound shift from mid-20th century information dynamics. The space age began in an era when governments controlled major observational assets and could maintain information monopolies more easily. Today, advanced amateur equipment rivals professional capabilities in many domains. Global communication networks allow instant sharing. Satellite imagery is commercially available. The information landscape has democratized in ways that make top-down containment strategies obsolete for astronomical discoveries. The balance between skepticism and openness becomes crucial for healthy public discourse. Extreme skepticism that dismisses all unusual observations as mundane or fraudulent prevents legitimate investigation of genuinely anomalous phenomena. Extreme credulity that accepts extraordinary claims without evidence enables misinformation and pseudoscience. The productive middle ground maintains openness to unusual possibilities while demanding rigorous evidence. In the specific case of 3I Atlas, transparency has been total because the object was recognized as a standard comet throughout the observation period. All data is publicly available. Professional papers analyzing the observations are published. Amateur astronomers shared their images and measurements freely. This represents science functioning as intended open, collaborative, self-correcting. If evidence had emerged suggesting artificial origin, that same openness would make containment impossible even if attempted. The first team noticing anomalous data would likely share it with colleagues for verification. Those colleagues would examine it independently. Within days or weeks, the information would circulate through professional networks. Someone would mention it in an online forum. Science journalists monitoring those forums would investigate. The news would break not through official announcement, but through grassroots dissemination. This isn't a failure of security protocols. It's the natural consequence of scientific culture and modern information technology. It's also probably healthier than controlled disclosure from authorities. When extraordinary information emerges from distributed, independent sources all reaching similar conclusions, it carries credibility that government announcements might lack, given historical context of secrecy around UFO-related topics. The question isn't really whether to contain or disclose information about confirmed extraterrestrial intelligence. The question is how to facilitate public understanding when that information emerges through decentralized processes. How do we ensure accurate context accompanies sensational findings? How do we prevent misinformation from overwhelming factual reporting? How do we help people process transformative knowledge productively, rather than descending into panic or denial? These challenges apply to any major paradigm-shifting discovery, not just extraterrestrial intelligence. They represent fundamental questions about how societies manage knowledge in the information age. The balance between skepticism and openness, between security and transparency, between protecting people and respecting their right to know, these tensions will define how we handle the next great revelation, whatever it might be. Let's step back from speculation about 3I Atlas, specifically, and contemplate the vast scales of space and time that contextualize any discussion of extraterrestrial intelligence and interstellar reconnaissance. These scales are so immense they challenge human comprehension, yet understanding them is essential for grasping what contact with advanced civilizations would actually mean. Our galaxy, the Milky Way, contains between 200 and 400 billion stars. Current estimates suggest that most stars host planetary systems. Conservative calculations indicate potentially tens of billions of planets in habitable zones where liquid water could exist. Even if life emerges on only a tiny fraction of these worlds, and intelligence develops on only a fraction of life-bearing planets, the numbers suggest we shouldn't be alone. But the distances are crushing. The nearest star system, Alpha Centauri, sits 4.37 light-years away. That means light traveling at 300,000 kilometers per second. The fastest thing in the universe takes over 4 years to cover the distance. Our fastest spacecraft, Voyager 1, has been traveling for over 45 years and has barely left the solar system, covering about 0.0025 light-years. At its current speed, it would take roughly 75,000 years to reach Alpha Centauri if it were headed that direction. Scale that to galactic dimensions. The Milky Way spans approximately 100,000 light-years across. From our position roughly 26,000 light-years from the galactic center, we occupy an unremarkable spot in one of the spiral arms. Radio signals from Earth have been leaking into space for roughly a century, meaning our oldest transmissions have reached stars within a 100 light-year radius, a sphere containing perhaps a few thousand stars. The timescales are equally humbling. Earth formed 4.54 billion years ago. Life emerged relatively quickly. The earliest evidence dates to at least 3.8 billion years ago, possibly earlier. But complex multicellular life didn't appear until roughly 600 million years ago. Dinosaurs dominated for 165 million years before extinction. Homo sapiens has existed for perhaps 300,000 years. Technological civilization, radio, flight, space travel emerged in the last century, a geological eye blink. Now consider, billions of stars in our galaxy formed billions of years before our sun. Planetary systems around those ancient stars could have developed life and intelligence long before Earth even existed. If even one civilization emerged a billion years before humanity and survived, their technological advancement would be so far beyond ours that comparison becomes meaningless. The difference between us and them would be vastly greater than the difference between us and bacteria. This is where the artificial gravity speculation about 3I Atlas gains interesting context. If an advanced civilization wanted to observe us, the engineering challenge of building a comet-camouflaged probe would be trivial compared to the challenges they've already solved, simply by surviving millions or billions of years. The rotation-generating artificial gravity wouldn't be impressive technology for such beings. It would be Stone Age simplicity, the equivalent of us using a lever or wheel. Yet the distances create profound constraints even for advanced civilizations. The laws of physics appear universal. Nothing travels faster than light. Even if you solve every engineering challenge, perfect propulsion, indefinite energy, century-spanning missions, you're still bound by light speed. A civilization 1,000 light-years away, observing Earth through telescopes, sees us as we were 1,000 years ago in medieval times. Any probe they sent in response would take at least 1,000 years to arrive, even traveling at light speed, which appears physically impossible for objects with mass. This creates what might be called the temporal barrier to contact. By the time signals travel between civilizations, centuries or millennia have passed. Species evolve, civilizations rise and fall, cultures transform beyond recognition. The beings who sent a message might be extinct before reply arrives. The civilization that launched a probe might have collapsed before it reaches its destination. Unless, of course, civilizations achieve stability spanning millions of years, something humanity has never witnessed but can't rule impossible. Or unless they develop technologies that sidestep our understanding of physics, wormholes, warp drives, or exotic physics we haven't discovered. Both possibilities remain speculative. The cosmic perspective does something interesting to the reconnaissance probe speculation. On one hand, it makes the scenario less plausible. Why would an advanced civilization bother sending physical probes across vast distances when countless other worlds surely exist closer to them? On the other hand, it makes it more plausible. With millions or billions of years to develop technology and explore, an advanced civilization might have distributed probes throughout the galaxy purely as routine science, studying as many worlds as possible without particular focus on Earth. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in our galaxy. It multiplies together factors like star formation rate, fraction of stars with planets, fraction of habitable planets developing life, fraction of life developing intelligence, fraction of intelligence developing technology, and the lifespan of technological civilizations. The result is highly sensitive to the final term civilization lifespan. If technological civilizations typically survive only a few centuries before destroying themselves, the galaxy might contain only a handful of active civilizations at any given moment, isolated by vast distances and poor timing. But if civilizations regularly survive millions of years, the galaxy could be densely populated with ancient intelligences, despite the fact that we see no obvious evidence. This is sometimes called the longevity filter. Perhaps the great filter isn't about the emergence of life or intelligence, but about the survival of technological civilizations long enough to become visible at galactic scales. Humanity stands at the threshold. We possess technology capable of self-destruction and haven't yet demonstrated we can manage it wisely over centuries. Whether we survive the next few hundred years might determine whether we join the community of long-lived civilizations or become another cautionary example of species that developed technology before wisdom. The scales of space and time surrounding any contact scenario create both hope and melancholy. Hope because the universe appears capable of producing intelligence. We're evidence of that. Melancholy because the distances and timescales might ensure that intelligences remain forever isolated, aware that others exist, but unable to meaningfully communicate or meet. If 3I Atlas represented reconnaissance, it would mean we're not isolated. It would mean someone bridged those distances, solved those engineering challenges, maintained civilizational continuity long enough to conceive, launch, and monitor an interstellar mission. It would prove that the barriers aren't insurmountable, that despite the crushing scales of cosmic space and time, connection remains possible. That possibility, that somewhere in the vast darkness, ancient eyes might be watching with patient curiosity, that the rotation of a comet might be deliberate engineering, creating gravity for instruments, studying us is simultaneously unsettling and profound. It means we're not alone in the night. It means the silence might not be emptiness, but patience. It means the cosmos, for all its inhuman scales, might contain companionship after all. Let's shift our tone towards something more optimistic, because regardless of whether 3I Atlas was a natural comet or represents something more exotic in our speculative thought experiment, the actual story of its observation represents something genuinely hopeful about humanity's scientific capabilities and collaborative spirit. The detection and tracking of 3I Atlas showcases human achievement at its finest. The ATLAS, Asteroid Terrestrial Impact Last Alert System, survey that discovered the comet operates telescopes in Hawaii, Chile, and South Africa, scanning the entire accessible sky multiple times per night. This system represents decades of astronomical development, international cooperation, and commitment to understanding our cosmic environment. That we can detect a relatively small object months before perihelion accurately determine its trajectory, and coordinate global observations demonstrates sophisticated capability that would have been impossible just decades ago. Professional observatories worldwide contributed data. The European Southern Observatory, Kit Peak National Observatory, Gemini Observatory, and dozens of others pointed instruments at 3I Atlas, gathering spectroscopic data, light curves, and images across multiple wavelengths. This wasn't competition, but collaboration, astronomers sharing data, comparing measurements, refining models together. National boundaries became irrelevant when facing questions about the nature and behavior of a fascinating cosmic visitor. Amateur astronomers made crucial contributions that deserve celebration. Individuals with backyard telescopes, privately funded small observatories, and passionate skywatchers documented 3I Atlas throughout its approach. They shared images online, contributed to light curve analysis, and participated in the global observation campaign. This represents democratic access to scientific discovery. You don't need a PhD or government funding to contribute meaningful data to humanity's understanding of the cosmos. The transparency of the process is equally remarkable. Discovery announcements went public immediately through the International Astronomical Union's Central Bureau for Astronomical Telegrams and the Minor Planet Center. Orbital data became available through JPL's Horizon system. Professional papers analyzing observations appear in open-access journals. Raw data from many observations sits in public archives. Anyone with interest and appropriate software can analyze the same data professional astronomers examined. This openness creates resilience against misinformation. When data is accessible, claims can be verified or debunked by independent analysis. Conspiracy theories struggle to gain traction when thousands of people worldwide have direct access to the evidence. The speculation I've indulged in this video about artificial gravity and reconnaissance missions remains speculation, precisely because the data doesn't support it. The evidence consistently points to natural comet behavior, and that evidence is available for anyone to examine. The institutional cooperation demonstrated during 3I Atlas observations extends beyond astronomy to space agencies, government science organizations, and international bodies. NASA provided trajectory analysis and risk assessment through its Center for Near-Earth Object Studies. ESA contributed observations from its telescopes and spacecraft. National space agencies worldwide participated according to their capabilities. This cooperation occurs routinely now, a normalized pattern of international scientific collaboration that would have seemed impossible during Cold War-era space race competition. The public engagement aspect deserves special recognition. Space agencies and observatories didn't just collect data privately, they shared updates, images, and explanations designed for general audiences. NASA's website featured articles about 3I Atlas accessible to non-experts. Observatories posted their images on social media. Science communicators created content explaining what sun-grazing comets are, why they disintegrate, and what the observations revealed. This represents a commitment to public science literacy and democratic access to knowledge. Even the speculation and questions raised by unusual objects like 3I Atlas serve positive functions. They encourage critical thinking about what's possible, what evidence would support various conclusions, and how to distinguish between legitimate scientific uncertainty and unfounded conspiracy theories. Teaching people to ask, what would we expect to observe if hypothesis X were true, and does the data match those expectations? Creates scientifically literate citizens capable of evaluating claims independently. The technological achievement underlying these observations is staggering when viewed historically. Humans developed complex telescopes, charged coupled device cameras, spectroscopic instruments, computer processing capable of analyzing massive datasets, orbital mechanics calculations, and global communication networks, all within roughly 1 century. We went from barely being able to photograph the moon to precisely tracking objects throughout the solar system, determining their composition from light analysis, and predicting their trajectories months in advance. The survival and function of this scientific infrastructure represents hope beyond the technical achievements. Despite global political tensions, economic challenges, pandemics, and social disruptions, the international scientific community maintained operations, funded facilities, and continued collaborative programs. Astronomers in countries with difficult diplomatic relations still share data, publish together, and work toward common goals. Science serves as one of humanity's most successful examples of international cooperation. Looking at our response to 3I Atlas and similar objects, we can feel genuine optimism about humanity's ability to handle extraordinary discoveries if they occur. We have frameworks for verification, peer review, international coordination, and public communication. We have communities of professional and amateur scientists motivated by curiosity rather than profit. We have technological capabilities that continue improving rapidly. We have institutional commitments to transparency and democratic access to knowledge. If we ever do encounter genuine evidence of extraterrestrial intelligence, whether through radio signals, artifacts, or something unexpected, the response will likely follow patterns established through observations like 3I Atlas. Multiple independent teams will verify the findings. International cooperation will coordinate analysis. Public communication will attempt to balance accuracy with accessibility. Speculation will run ahead of evidence, but the scientific process will eventually sort truth from imagination. The artificial gravity speculation we've explored throughout this video, while unsupported by evidence in this case, represents healthy scientific imagination. Scientists regularly consider exotic possibilities as thought experiments to understand what evidence would support various conclusions. The fact that we can imagine advanced civilizations using rotation-generated artificial gravity for reconnaissance missions, then examine whether 3I Atlas's observations match that scenario, demonstrates scientific reasoning functioning properly. The answer in this case is clear: natural comet. But asking the question exercises the intellectual muscles we'll need if we ever encounter genuine anomalies. It forces us to think about what artificial objects would actually look like, what evidence would distinguish them from natural phenomena, and what level of proof should be required before accepting extraordinary claims. We learned valuable things from 3I Atlas beyond confirming it was a comet. We refined models of sun-grazing comet behavior. We gathered data on disintegration processes near perihelion. We tested observation networks and coordination protocols. We engaged public audiences with explanations of orbital mechanics, spectroscopy, and solar physics. Every observation campaign, even of perfectly ordinary objects, builds capability and knowledge for future discoveries.